Shiloh, I think you're on mute.
Sure am. Thank you for that, Christina. I do want to welcome and thank you all for joining us for the first webinar in the 4-part webinar series, Technology and Innovation in Wind and Wildlife, co-hosted by the Renewable Energy Wildlife Institute and the National Renewable Energy Laboratory, and supported by the U.S. Department of Energy's Wind Energy Technology Office. I'm Shiloh Felton. I'm a senior scientist for Renewable Energy and Wildlife Institute, and I'm really excited to see you all today. The first webinar, The Future of Wind Energy Technology and Wildlife Considerations, focuses on the state and direction of land-based wind turbine technology and its implications for wildlife. As wind turbines grow in size, including taller hub heights and longer blades, and become more efficient at relatively low wind speed conditions, the types of wildlife impacted and the nature of those impacts may change. This in turn may also influence how we monitor and minimize wind energy and wildlife interactions. As I said, this is the kickoff webinar for a 4-part webinar series. The following 3 webinars will take place over the next few weeks. Technology acceptance workshop results from the bench to the field will take place Tuesday, January 31st from 3 to 4 p.m. Eastern. Technology acceptance workshop results acceptance will take place Thursday, February 9th, 4 to 5 p.m. Eastern. And Wind Wildlife Research Meeting Technology and Innovation Discussions Continued will take place Thursday, February 16, 2 to 3 p.m. Eastern. You'll need to register for each webinar separately, and Christina Marshall is going to post the link to register in the chat for all of us. Each webinar will be recorded, and recordings will be posted on the webinar page. Just some quick logistics before we get started. Please submit any questions to the chat feature. We have a Q&A session after all speakers have presented. You can enable closed captioning on your Zoom screen. And if you experience any technical difficulties, please email Christina Marshall. And Christina is going to put her email in the chat so that it's available after I leave this page, this screen. I'd like to welcome the speakers for today's webinar, The Future of Wind Energy Technology and Wildlife Considerations. First, we'll have Eric Lantz, a senior analyst and group manager at the National Renewable Energy Laboratory, specializing in wind power policy, markets, and technology. Next will be Sarah Weaver, who's a principal and natural resources director at Bowman Consulting, where she manages a team of ecologists who provide environmental and permitting assistance to commercial and residential developers across the U.S. Misty Sporer is the Environmental Development Director for Duke Energy Sustainable Solutions. She and her team provide environmental siting and permitting support for the development, construction, and long-term operations and management of wind, solar, and battery storage projects throughout the entire U.S. Thank you all for being here today. Eric, you're kicking off the presentations today, so I'll turn it over to you.
Great. Thank you, Shiloh. And share my screen. One more step here. All right, hopefully that looks good. Christina, let me know if you're seeing anything incorrectly. Like Shiloh said, my name is Eric Lantz. I'm with the National Renewable Energy Laboratory, and I spend a great deal of my time thinking about the future of wind technology and how innovation is going to change the wind sector. And so hopefully I can give a good foundation here at the outset of this webinar series. And of course, the following speakers will build on and flesh out much more of what I'm going to be able to get into. Just a few quick highlights from my remarks. If I drone on too long, or if you just like the Cliff Notes version. In terms of the size of wind turbines, that's probably the most obvious significant technology change that you can see out there on the landscape. Today, turbines are at roughly 500 feet. Obviously, turbines that were installed, in years past might be shorter than that, but typically today you're looking at a system or a turbine that's about 500 feet. In the future, those heights are probably going to go up, potentially as high as 700 feet for onshore turbines. And for those of you that might dip a toe into the offshore sector, even larger there, potentially as high as 900 feet. One of the things that I'll look to highlight a little bit here, this is a little bit beyond sort of turbine technology specifically, but when we think about what the future of our energy system and electricity sectors are going to be, and we look at sort of zero carbon scenarios out there in the future, or even low carbon scenarios, wind is going to play a big role, 30% to perhaps even as high as 50%. One of the things that's going to be a determining factor in what role it ultimately plays, though, is going to be siting challenges, including the ecological and wildlife challenges. And so I'll give you a little bit of a sense of how, different ways that might influence the ultimate build out of wind energy. If you are trying to understand like what might be the balance of onshore or offshore wind energy, I'll just touch on that super briefly because I know this webinar series is focused on land-based technology, but we anticipate offshore wind to be roughly maybe 20 or 25% of the overall wind sector. So the vast majority of future wind deployment is still expected to be onshore. Of course, if we have a lot of difficulty siting onshore turbines and facilities, that might push more into the offshore domain. I was asked to speak a little bit too about sort of non-traditional wind energy technologies, of which they take various forms. And I would say the thing there is that many of them are functional and viable, but they have a hard time competing with the economics of sort of the mature systems of today. So really getting that cost down and then having a proven track record. Oftentimes wind facilities are hundreds of millions of dollars, perhaps even billions of dollars in the really large facilities. And so you have to have a proven track record in order to get financing and bring a project to fruition. All right, so just digging into the details a little bit more here. These plots show changes in typical turbine system pieces. So on the upper left-hand side, you have hub heights. Those are approaching, not quite there yet, but sort of approaching the 100-meter mark. So the tower itself and the nacelle that sits on top of it there is about 100 meters. On an average rotor diameter basis, we're looking at numbers that are sort of in the 130-meter domain. Of course, there are systems that are taller and have larger rotors, as well as systems that are smaller and have smaller rotors. These are the average values, but you can see that there's been steady increases in turbine size across the board here. In terms of nameplate capacity, we're now up to turbines that are on average about 3 megawatts per turbine. One other parameter that's shown here on the lower left-hand side is specific power. This is the ratio of the rotor and the generator, and a lower specific power means you have a relatively larger rotor and a relatively smaller generator. You've seen actually rotor growth driving significant reductions in specific power for much of the past decade. More recently, though, we are seeing movements to bigger nameplate capacity turbines, and so you're seeing a little bit of an uptick in the specific power there. Just to try and visualize some of those changes in turbine sizes, this was from a study I worked on with some colleagues from Lawrence Berkeley National Laboratory a couple of years ago. We queried experts from around the world on what they thought sort of average turbine sizes might be in 2035, both for land-based and offshore applications. Again, you can see where we were in 2019 in terms of some of the average rotor diameters and hub heights, a little bit smaller than those numbers I quoted you just a moment ago. That's a reflection of growth in averages over the last 3 years. By 2035, though, there is anticipated to be even more growth in sort of the average turbine sizes, up to 130 meters in hub height, 174 meters in rotor diameter, and nameplate capacities at the 5.5 megawatt level. One of the other things that in this limited time, I won't be able to go into great depth on, but is we do anticipate changes in the way plants are designed and laid out. Essentially, right now you might have a plant with all the same turbines, sited in fairly optimized arrays, but with all the same turbine types. In the future, you might expect different sizes of turbines within a facility, really designed to sort of maximize energy extraction from a given piece of land. We also anticipate better able to control the plant as a unit. You can sort of think about an orchestra and how you have all the different parts of the orchestra doing what they're supposed to do at the right time. We anticipate that's the way wind plants could operate in the future as well, which is obviously something that could be a benefit for wildlife management. All right, moving quickly ahead for the sake of time here. When we think about technology, one of the key drivers are the siting considerations. I touched on this in the highlights. We track and we have a database of ordinances on wind energy facilities. This is a snapshot of what's in place today, overlaid against the existing wind fleets. And you can see that there's a pretty strong correlation between communities and counties that are encountering wind energy and the development of regulations and ordinances that might govern how wind energy exists within those localities going forward. This is only focused on sort of setbacks and kind of typical community-based ordinances. You also have to think about, obviously, environmental and wildlife interactions, and then also airspace interactions. So when the turbines are reaching up to 700 feet or more, obviously there could be airspace conflicts that we have to manage too. What's shown on the map on the right-hand side is just the more setback-based ordinances. There's a growing concern and something that I think that the technology is going to have to work to be better integrated into these communities in order to navigate and manage around community concerns. I'll just buzz through this quickly. This is a reflection of some of the potential future build-outs. When you think about relatively open access to siting versus limited access to siting versus reference conditions, when we have more restrictive siting scenarios, we see a little bit less wind energy deployed. And when we have relatively open siting conditions, we see more wind energy deployed. But one of the things you see, these sort of horizontal lines across, you have the capacity deployed on the top plot, and then the percentage of generation on the bottom plot. Basically, you're looking at a number perhaps as high as 500 gigawatts of wind energy or more. As we go to lower and lower carbon scenarios, as the bars move to the right, you're going to more restrictive carbon scenarios over the long term, 2050 there. And you're looking at probably 30% of our electricity generation coming from wind energy. Again, that could be as high as 50% or even more so in very low carbon futures, 95% carbon reduction scenarios, or even a zero carbon economy of the future. So what is this going to look like, and how is the technology and wind plants going to be interfacing with wildlife concerns? We have a snapshot of where wind turbines were installed in 2020 on the left-hand side. And then if you have a 40% wind scenario, so that's sort of between that 30 and 50% range that I mentioned a moment ago, you're looking at a scenario with 550 gigawatts of wind energy spread in this way across the contiguous United States. Now, this is just one scenario. It's tied to our reference siting conditions and sort of the local economics and where load growth is forecast. But this is one way that build out could play out to get to a 40% scenario. Under relatively open siting conditions, we actually are able to build larger, sort of more dense plants to a large extent in the interior of the country. And then you can see some facilities sort of on the eastern seaboard there. Again, that's a reflection of relatively open access siting conditions. If you have more limited access, you actually have to take those plants and chop them up into a lot smaller pieces. And so the footprint of the facilities is actually bigger. You're also developing in lower quality resource areas, so you end up needing to build more capacity for a given amount of wind energy generation. So there's just some of the ways the technology and the deployment could interact with one another, and then obviously with implications for wildlife. Just super quickly on the offshore front, we've run a lot of scenarios around offshore wind. One of the key things is it is sensitive to how easy or difficult it is to site land-based facilities. So restrictive land-based siting conditions push more offshore. Open siting conditions onshore mean you might see a little bit less offshore wind, primarily because of cost. It's just a little bit more expensive to build offshore. What you can see here is sort of, if you look at the very high level at the plot without getting into all the details, we're looking at scenarios between 100 and 200 gigawatts of wind energy out there in the future. When you go to those 95% or even zero carbon scenarios, you're at the sort of 700 gigawatts to maybe a terawatt of wind energy. So that's how you get to sort of the maybe 20% number as a market share of overall wind capacity from offshore. Last slide, I think here is just a final word on some of the other technologies. Everything that you see out there in the market today is sort of the three-bladed horizontal axis upwind turbine. Of course, there are distributed applications. So this is how you might see different sizes of wind turbines, residential scale to to community scale. And then there are airborne and kite solutions, as well as vertical axis platforms. And you may have seen some of these bladeless wind turbines that kind of vibrate out there in the wind. Again, like I said at the outset, really the key question for those technologies is, what does it cost, and can it be scaled to sort of a commercial level? And is it going to provide the proven track record that you need in order to get, the large scale financing that's required for hundreds of millions of dollars of investment, and ultimately at the national scale, billions of dollars of investment. I believe that's all I have, and I think I took about 1 extra minute, but I'll wrap it up there and pass the baton to our next speaker.
Awesome.
Go
good
ahead,
afternoon,
Sarah.
and thank you, Eric. Can everybody hear me?
Yep, you're good.
Great. I'm going to share my screen. Okay. I think it should be showing well. Again, Christina, if anything is not looking right, let me know. I am going to keep my camera off for internet stability purposes, though. So let me do that real quick. Awesome. Okay. Good afternoon. And again, thank you, Eric, for the excellent introduction to how turbine technology is evolving. As mentioned, my name is Sarah Weaver, and I'm the Natural Resources Team Lead at Bowman Consulting. And for this webinar, I'm going to expand on what Eric just presented into what this means for wildlife monitoring and fatality minimization efforts. So as the turbines become larger, expand into new areas, as well as increase in number on the landscape, this really creates many questions on the monitoring and minimization fronts for wildlife. And that is what I want to cover with this talk. What are the new questions we should all be asking, and how will we answer them? I definitely don't have all, if any, of the answers, but want to use this as an opportunity to help us all start thinking about them. And one of the first questions that comes to mind when listening to Eric is, what will the taller wind turbines with larger rotor diameters mean for fatality monitoring? Do larger turbines mean that birds and bats hit by the blades will fall further distances from the turbine, which leads to the question, do we need to increase search areas? And if you look to the literature, there are mixed results. Choi et al. Found that for birds, there is some evidence long distance migratory birds may be found farther from turbines than short distance migrants. And turbine size is positively influenced from fall distance of birds and bats when they were analyzed together collectively, and for birds when analyzed separately from bats. And this would suggest that as turbines increase in size, a greater search radius will be necessary to detect carcasses, particularly for the larger birds, such as eagles and raptors, because fall distribution is also influenced by body size. The larger the animal, the further it may land. But larger animals are also easier to detect, so maybe we need adjustments to search protocols, such as what was suggested in Hollingstad and others in 2018 for eagles. The answer may also depend on if you are searching roads and paths only or full plots, like seen here on the left. For a full plot, a larger search radius means more time and money, and the return on the additional area searched may not justify the increase. Increasing the search radius of road and pad only searches doesn't really add much additional effort and could be easier to implement. Whether smaller birds and bats will fall further from the turbine also largely depends on wind speeds at the time of the strike and where along the blade a bird or bat is struck, and if the blade is on an upswing or a downswing. If they are more likely to be struck in the middle portion of the blade, let's say, or closer, they would likely fall closer to the tower, same as if they are hit closer to the nacelle. So fall distribution data from monitoring and models suggest that the majority of carcasses actually do fall closer to the turbine, and estimators like GenEst account for search area and fall distribution when estimating mortality rates. What seems to be more pressing is ensuring our estimates are comparable across sites and regions, which had not been the case until more recently, because most are now calculating density weighted proportion of carcasses found and using GenEst, which allows us to really compare apples to apples. Next, should we continue to search every site? And this was a topic that was brought up at the Wind Wildlife Research meeting this past November. Traditionally, we have monitored at all individual wind farms. Often though, neighboring wind farms or even those that might be in the same region have very similar results for mortality rates as well as the species composition. So the time and money spent monitoring new wind farms in regions where we have good data could potentially be put towards things like minimization or research on how we might be able to switch to a more regional monitoring effort instead of monitoring at every site. This will be increasingly important with the predicted number of wind farms in the future build out. Additionally, as turbines shift higher into the airspace, will this change what species are impacted? Maybe we think we know everything for a particular region, but in fact, larger turbines will mean that we don't. Another consideration is how larger turbines will influence other technologies used for monitoring, such as cameras for behavioral studies. A single camera, thermal camera, already can't cover the entire rotor swept area of a wind turbine today. And different focal lengths of lenses means different fields of view. It will be important for groups studying animal behaviors to consider how much of the rotor swept area they need to view, and if multiple cameras might be necessary with taller, larger turbines. The image here, made by Brogan Morton, who will be presenting next week, shows the field of view of two different lenses. They each sample the same volume, but will provide very different views of the area in and around the rotor sweep. So this is important to consider with larger turbines. There are also new questions about established minimization strategies. So taller, larger turbines means that they are better able to produce energy in low wind speeds. And wind farms are now being constructed in areas where wind energy was once considered not viable. And this is great for increasing renewable energy. But what does it mean for curtailment as a minimization strategy? Curtailment reduces fatalities for some birds and most bats by restricting when a wind turbine is operational. And for bats, this works at night in low wind speeds, which is when we see peaks in bat fatalities. The most common wind speeds that turbines are shut down are under 5 meters per second and 6.9 meters per second, depending upon the reason why the curtailment is being implemented. So in these low wind speed areas, this could mean that wind turbines at a facility wouldn't be curtailed most of the night, resulting in greatly reduced power production and possibly resulting in locations no longer being commercially viable. Then there are ultrasonic deterrents, which use sound to deter bats. Ultrasound attenuates quickly, and there are already questions about their effectiveness at certain distances. So as blades become longer, will they continue to work for those species and in those places where they have been previously effective? Maybe it's simply a matter of where they are mounted and testing new configurations, such as tower-mounted deterrents. There is new evidence suggesting that bats are highly active below the rotor swept area, which might mean we should mount deterrents lower. But now for potentially good news. Larger turbines could mean that it takes fewer of them to produce the same amount of energy and a reduced wind farm footprint. So a site that once produced, or that would produce 400 megawatts from 202 megawatt turbines could produce the same amount of energy with half that many, which reduces indirect wildlife impacts to the landscape and habitat, and possibly direct impacts as well. We don't really know yet. As an example, a 55-meter blade length is about 9,500 square meters of rotor swept area, whereas a 70-meter blade length for a turbine that can produce twice as much energy is about 15,400 square meters. So less than double the area covered by the rotor sweep, but half the number of turbines are required. So what are the answers? For many of these, I don't know, but I have ideas on how we can find them, and maybe some of you do as well. The important part is that we are thinking about them and working towards finding solutions. This is also not an exhaustive list of questions needing answers, and I am sure many of you have thought of others, which I look forward to hearing during the Q&A session. I do want to thank NREL and REWI for inviting me to speak and for putting on this important webinar series. This is my contact information, and I encourage anyone interested in working to find solutions to reach out to me. Thank you. And now I'm going to pass it off to Misty Sporer with Duke Energy.
Thanks, Sarah. I'm going to attempt to share my screen here, so bear with me as I get going. And we'll click the share and hope it all works out. Okay. Well, hello, everyone. I'm Misty Sporer. I'm the Director of Environmental Development at Duke Energy Sustainable Solutions. And I wanted to kind of take a step back. Both Sarah and Eric did a really good job of presenting a lot of highly technical information. But I think in order to really explore this question, sometimes we need to go back to the basics. And one of those is, how does a wind energy center or wind farm end up on the landscape? How do we end up putting turbines where we put them? And so as we've alluded to in the conversation, it really depends on where the wind is, right? If you're going to produce electrons from the wind, you need to be where the wind is. And historically, we have looked at wind speeds about the 80-meter height, and typically industry has looked for annual average wind speeds of about 6 or 6.5 meters per second in order to make a wind farm viable. With the technology advances that Eric mentioned and the conversation about higher up, longer tubular steel supports, therefore making a hub height greater, we are seeing a decrease in the wind average speed that makes a plant viable. So up on the screen, you should be seeing a couple different maps generated by NREL. These are all available online. There's the link on the slide there for where you can find these maps. But I'm using them to illustrate a point, and that point is that we have historically looked at certain places on the landscape for high productivity wind sites. As our hub heights increase, the area of the US that becomes available for high quality wind increases. So in the upper right-hand corner, you'll see a map of 100-meter hub height wind speeds, and you'll see the dark blue areas being the highest wind speeds all the way down to the sort of light yellow color being low wind speeds. And you'll see that that changes as you go up in meters. So you have 100-meter up there on the right-hand corner. Down in the lower left, you'll see the wind speeds at 140 meters, and then you'll see them at that 200-meter mark. And the point of these slides is to show that that wind speed changes, and therefore our wind resource changes as our technology changes. But this also creates a situation in which we have differing wind speeds at differing heights, and that can create some technology issues that we have to deal with in the form of wind shear. And we'll talk a little bit about wind shear later on in a later slide. But we've kind of really had a great slide from Eric showing the hub height differences. I think that was a perfect visual when we do talk about what does it mean when the hub height increases. It gives us access to these additional wind resources, but it also creates a taller tower. And that has implications that we'll discuss a little bit later. So when we talk about wind, not only do we look at the quality of the wind resource, we look at something called a capacity factor. And that's a number that's a theoretical construct, right? How much wind does it take to generate electricity if the turbine spends 100% of the time at its 100% efficiency rate, right? But for wind turbines, we know it's not 100% efficiency, right? There's something called the Betz limit. So I'll let you Google the Betz limit and find the equation for that. But there's a limit to how much electricity can be produced per turbine. So that maximum output then has efficiency factors, right? And that plays into a capacity factor. So there's a lot of math that goes into figuring out just how many electrons we can get out of a turbine in any given location with the number of hours it may run. And as we all know, the wind doesn't blow all the time. So different wind regimes have different capacity factors across the landscape. So you may have a site with really high winds, but those winds, or really high quality winds, but those winds don't blow all the time. And so that's going to change your capacity factor. You may have a site that has low wind speeds, but very, very, very consistently, and that's going to give you a different capacity factor. So those are elements that we look at when we go to site, and the hub height and technology changes are going to change the way we look at that. There's also something called the grid, right? We have to make these electrons, but not only do we make them, we have to ship them out to where they're needed. And that's going to require an interconnection to the transmission grid. Typically, commercial, what we consider generation style wind sites connect at 69 kilovolts or higher, so a 69 kV system or higher. Typically, it's higher. And those transmission lines are governed by a lot of different entities. There are regional transmission organizations or RTOs, there's independent system operators or ISOs, and then there are parts of the United States that aren't covered by either of those style of entities, and they have a non-wholesale power market or power exchange, which is accomplished with different MOUs or agreements, service agreements between the different transmission operators in those areas. Each of these types of systems has restrictions and requirements and sort of a long line of projects that they're waiting to evaluate for interconnection. And that long line of projects is oftentimes referred to as the queue. So you enter the queue with a project, you're going to generate so many megawatts of electricity and you want to connect to the grid. There's a bunch of studies that take place, but they can't do these studies all at once. They're done one after another sequentially. And those types of studies take time, right? And so you've got a long line of people waiting in the queue for those studies to happen. And each study builds on another. So you assume one project gets built. By the time you go to analyze the next project, you've assumed one or two projects before have been built. And that has changing dynamics on the way electrons are going to flow across the system. And so these different organizations, these different entities have to talk to each other. They have to plan together, and they have to organize their queues. And believe it or not, that's a messy process, right? You get a lot of people and a lot of organizations together, a lot of different studies that take place, and you get kind of a messy system for interconnection. But without that interconnection, no place to plug in, the wind farm is not economically viable. If you cannot sell your electrons, you can't put them to use, you can't build a wind farm. And so interconnection agreements and power purchase agreements are also two components to this complicated system that oftentimes dictate where we can and cannot put these things on the landscape, or where we successfully install wind energy on the landscape. So I think the point of this slide is to say it's complicated. There's a lot of different reports that go into siting and locating wind farms that have absolutely nothing to do with wind resource or the landscape itself, but simply the transmission grid. This slide is for illustrative purposes, just to kind of drive home what we've been chatting about. In the upper photo or image, you'll see the gray bubbles. Those are existing wind farms on the landscape. And you'll see a purple map of our transmission grid in the lower corner. And as we overlay them, you will see that generally wind has been built to date on places where there's good transmission infrastructure. So places where there are power lines and good wind resource to ship those electrons to market. So what does it mean when their technology changes and you're able to harvest wind in a different spot, maybe, the less dark blue spots on the map? Are we able to utilize some of these other dark purple lines, these other high capacity transmission lines, in order to get electrons to market? And the short answer is maybe. It just so happens that we also have land use constraints, right? And so private land, federal land, and environmental factors all play into where these things can go on the landscape as well. And so in the images, you'll see kind of a map of private lands in each US state. Lands that are dark green have very low private land relative to federal land, and those that are red have high private lands relative to federal land. So you'll see, kind of through the center of the US, those states have a lot of private land available. And private land is oftentimes where you see wind farms sited, and that's that the turbine manufacturer or owners, operators don't own the land, but rather lease the land from underlying landowners. So farms stay in the family, acreage stays in the family, the wind pad is leased, the wind site boundary is leased. And that often is an easier transaction on private lands than it is on publicly funded lands or publicly owned lands or even federal lands. The permitting process is different on private lands than it is on federal lands, and compatible land uses can also be different when we look at federal land versus private lands. And so the point of this is to illustrate, private lands are highly attractive for a multitude of reasons, but with private lands come community sentiments and non-participating landowner sentiments in and around your site. Federal lands obviously have multiple use mandates for a lot of the federal lands in the West. So if you think about BLM, there's multiple mineral use, oil and gas, recreation, wildlife, scenic beauty. There's all kinds of different factors that need to be balanced out on federal lands that may make that a little bit less of an attractive site for some development. And environmental factors, right? We talk a lot about species. We're very focused on wildlife, but there are non-critter resources, believe it or not. So as a wildlife biologist by training, it's hard for me to think about the other resources, the non-critters, but there are cultural resources. There are waters, there's certain soil types, vegetation types that are highly important to the thriving ecosystems that we have to take into consideration. And then there's the landscape scale consideration as well. Where are these things going in, a big landscape scale context? It matters on the scale of things. And the lower map there is just for reference as well. It's land use values. And so sometimes it can be a really attractive site for wind. You might have an interconnection right there ready to go, but your land rent is really, really high. And there are places in the US where land costs, the amount it takes to rent an acre to put a turbine is prohibitive. And so that's a reference point as well. So what do we do with these technology decisions? How does this influence? We talked a little bit about the turbine changes with hub heights, right? We can change our production factors. Lower wind classes suddenly become more economically viable, and we can expand the areas in which we are looking to develop these wind energy centers. Turbine manufacturers, there are a lot of manufacturers out there. There are 3 primary suppliers here in the US, but they all have various turbine models, makes and models for the different wind classes. So wind is rated class 1 through 4, and they have different models that can take advantage of that wind resource in its class to the fullest extent possible. So there are different features, like when you buy a car, different manufacturers have different features that come with their makes and models. And there's different software packages and features that go into the decision to purchase one turbine over another, or maybe perhaps a certain turbine height over another. And a lot of those factors have to do with supply chain and deliverability, the software features. Does this system play nice with the grid operator system? Are there easy controls for the site to shut down or curtail the turbines as needed? You know, what kind of braking package and maintenance package do they come with? These things are mechanical in nature, so eventually they're going to fail. It's inevitable. And so there's service offerings and performance specs that go into the decision as to what kind of turbine and what application. And each individual company makes its own decision. You know, sometimes a company has historically purchased one type of turbine over another, and they have some operations and maintenance synergies by continuing to purchase that type of turbine. Companies have internal track records and experiences with different turbine types and software packages and the functionality of the turbine within their own system. And so there may be decisions on maintenance cycles or just familiarity of turbine techs with a certain technology. And then there comes purchasing power, right? If you buy 1,500, you may get a better price than if you only buy 7. And so sometimes that power of purchase can drive some of these decisions as to what kind of technology is deployed and where. And we've talked a lot about these land use changes, right? Hub heights. We've talked about the tower support. These things have to go on a tubular steel structure so that nacelle and those blades sit on top of a very robustly engineered tube. And that tube has to be constructed using a crane. And the taller these get, the bigger the cranes have to get, the more construction materials we need, and the longer it takes to get these things delivered to your site. They can only be broken into so many sections, and sometimes you can't drive a semi-truck loaded with a turbine blade down a county road. And so the material deliverability is important in this. You know, Sarah touched on her presentation. Number of turbines per project. Does that mean we get fewer turbines as these megawatt nameplate capacities get bigger? Does that mean we get more production out of fewer? And the answer is maybe. We have to consider turbine wake. So each of these turbines in a string influences the way the wind flows over the next across the landscape, and turbine wake can have some impacts on how turbine strings are laid out and designed. Catastrophic failure distances matter, right? These things get taller, the fall distance gets bigger in a radius around the turbine, and so they have to be sited for safety, not only for the turbines themselves and safe operation, but for stakeholders, setbacks, county requirements, homes, fences, all of those things go into play. So as these turbines get bigger, they have to be spaced out further, and while that may mean individual turbine footprints are smaller, overall sites maybe get bigger. And so the question of does this mean a smaller footprint, and the answer being maybe is you know, nuanced. Interconnection requirements, right? Megawatt increases, you're going to have a larger generation site wanting to interconnect. That's going to have different implications for grid. It's going to have possibly, you know, different requirements for substation. You may need to have something called a BOP, right? It's this term, plant, basically the systems of a power plant needed to deliver energy other than the generating unit itself. So substation upgrades, control equipment upgrades. So that balance of plant factor matters for these interconnections as these nameplate capacities get bigger. More interconnections, more upgrades, and less other generators come offline. And so Eric had a slide that showed, you know, our low carbon, zero carbon future. What does that mean for coal and natural gas sources? Does the landscape change as we begin to put more wind and less fossil fuel? What does this mean for solar? You know, as we begin to build out solar across the landscape, that changes the nature and structure of our grid as well. And capacity factors shift, and the usage patterns shift, and the productivity shifts, which is why batteries play a key role in this. So as we begin to diversify the types of renewable energy on our grid, we have different impacts to our system that require different upgrades to the system. So a lot of these things are interwoven, they play together. So what do we do about it, right? So I'm going to be a little punny here for a moment and say we rotate with it, right? Instead of we roll with it. We're going to rotate with it. Change is always a constant. There is nothing guaranteed about any of this, right? Energy in and of itself is dynamic, and the production of it is dynamic. So change in our industry is constant. We need to be flexible, we need to be innovative, and we need to work together to have these conversations. And supply and demand are going to drive a lot of this. So how do we work together? And that's a conversation I think Sarah, Eric, and I are going to explore a little bit in our open conversation here, taking your questions. But I do want to say, there are multiple stakeholders and many voices that are needed at the table. I think we have a good representation today between Sarah, Eric, and myself of different perspectives on how the industry is changing and shifting. And wildlife is important, but how do we balance birds and bats, right? How do we balance native ecosystems and landscape structure and soil types and prime farmland against the need for electrons? And so I think this is a dialogue that we hope to continue. And I'm grateful for NREL and REWI opening the channels for this conversation and allowing us to continue. So I just want to say thank you. And with that, I will stop sharing and allow Shiloh to continue her moderating.
Thanks for that, Misty, and to Sarah and Eric, all three great presentations, really, really informative. So great, you've all put your cameras on, perfect. I'm going to start with a question that started to generate a little bit of conversation in the chat already, just because it's probably one that's on a lot of people's minds. There was a paper by USGS and other partners, USO et al. 2021, that generated quite a stir to just opening the discussion or reopening the discussion about how size of turbines changes the scale of the impacts to wildlife. And there have been a lot of studies previous to that one, but I'll open it up to Sarah if she can comment on, how does turbine size overall affect impacts with wildlife?
Yeah, thank you for posing that question, Gary and Jordan. And there was a study from USGS that showed that repowering a facility didn't actually decrease. Putting in bigger, larger turbines didn't change the fatality. And so it was more of a, the overall energy produced by a facility was actually the better indicator, to my understanding, of what the fatality rate would be. And I think that was, like you said, very interesting and maybe not what some folks expected. I think it's a very mixed bag. I don't know that any one site in particular is going to be the same overall everywhere. There's so much variability in what we see by species, by location. And a lot of these studies, they actually find when they use site as a random effect, that it accounts for a lot of the variability itself. So while that may be the case for that one particular study, I'm not certain that would be the case overall. But I also think about the fact that we are just in general impacting less area if we have fewer turbines, and that indirect effect of having maybe a smaller footprint on the landscape itself and taking out less habitat is also just as important too. So I do think that it's a topic that is not completely resolved, but again, is one of those questions we need to be asking and finding ways to answer.
Thanks for that. Does anybody else have anything they want to add?
I would just underscore what Sarah said at the end there about sort of taking the system perspective. I think you can analyze impacts on a plant level, but at some level, when I think about society as a whole, like I'm more concerned about what the wind fleet is doing to wildlife than what any single plant is. And so if you really can change the footprint and the numbers of interactions and the locations of interactions of the fleet as a whole, you might actually be able to have a bigger impact than focusing on an individual facility. I think that's a great point, Sarah.
All right. Well, and along those same lines, this is sort of to both Misty and Eric. Eric's slide suggested that, and correct me if I'm getting this a little bit wrong, but suggests that an open access scenario would actually concentrate future development in states along the East Coast. But a restricted build out would scatter projects, with what looked like a majority of projects located near or along the wind belt, where there are already a lot of constraints. But that is where wind resources are highest.
Yep.
So I'm wondering why an open access scenario would place more wind energy projects, wouldn't place more wind projects along the wind belt. And if that's maybe due to factors like cost or transmission availability that Misty brought up.
Yeah. So just super quickly, I mean, off the top, I'll say that anytime you're trying to visualize these things at sort of the 48 state level, resolution is a real problem. And so actually if you had a drone and you could zoom into these places, you're seeing fewer, more dense, larger facilities in the interior wind belt in those open access sites. And the idea there is that, yeah, if you have open access, you're going to try and just gather the economies of scale that you can get from a bigger project, spread your fixed cost over a larger number of turbines, try and maximize the amount of energy you're extracting from a given chunk of land, and you'll have those bigger plants. The reason you see the development on the East Coast in the open access scenarios that it is assumed to be a relatively open access, easy to site sort of environment. In those regions, it's probably modeled as easier to site than what it is in reality today. I mean, you do see a few coastal Carolina, wind facilities, right? So they do exist, and it's sort of if it was easy to site, you would want to put more facilities along that part of the eastern seaboard because it is close to load. There's good transmission there, and the resource is decent. It's not great, but with the cost of turbines coming down, those sites are ostensibly commercializable. But I think that's where the siting piece is. There's probably a little bit of a disconnect or dissonance that shows up because it's an easier to site future than what we have today right now in those regions.
Misty, do you have anything to add there?
I think Eric did a great job of explaining that. I think one of the key pieces to this that I don't want to leave out of the conversation is transmission capacity, right? It matters where your need is, and it matters where your generation is, and how far those electrons have to go, or what type of upgrades to the system are needed. And the closer you are to your load, the easier it is to get the electrons to the right place. And in terms of overall cost, it's not free to plug into a transmission system, right? You pay to move your electrons on transmission systems you don't own. And so the further you are from your load, the more you pay to move those electrons along. So there are economies of scale. There's also basic economics. There's infrastructure, right? The way you can get materials to the site. If you've got a lot of interstate interconnectivity, you can get those materials on site. If you've got big cranes in the area, it's easier to get them out to the site and build your stuff. So it's a large ball of wax that's not easy to tease out what happens when you change one small factor when you've got 400 factors in your model.
And just to add to that complication, right, how does the addition of solar energy and storage capacity change these outlooks?
Right, that's a great question. And so when you look at the way our grid operates now, right, we have some generation sources that are what we consider on demand, right? You want some electrons, you fire up your natural gas power plant, in a few minutes, you're generating some electrons. And those types of resources, as they become fewer, or as we get less carbon intense in our infrastructure, we're going to have ups and downs, right? Wind farms have peak production, solar farms have peak production hours, and those don't always sync up when we get home and want to start cooking dinner, or in the morning when we get up and want to turn our coffee pots on, right? So our use doesn't always correspond with the production. And the more we have resources that are not as on demand as maybe some of the fossil generation, we have different balancing requirements, right? It's not undoable. It's very, very doable. It just requires a grid that's better integrated, that talks to each other better, more seamlessly, that allows for those electrons to flow where they need to go when they need to go there. And battery storage can add some reliability and robustivity to the grid in allowing us to have an on-demand resource that can be repowered when we are generating electricity from the sun or from the wind, that can be used when maybe the sun goes down or the wind stops blowing. So I think it's important to recognize that the grid plays a big role in this and that it's not just one isolated resource.
Thanks for that. You were just reminding me of times in my life when I was being asked by my public figures or whatever to reduce my laundry or other high energy usage in the middle of the day, right? And push that to non-peak times. So we've talked a lot about turbines getting larger and how those get into higher elevations, right? So what's happening lower down as turbines get bigger? Is the minimum height at which turbine blades are reaching is that changing at all as turbines are getting bigger?
I think it's important to recognize too, we're talking a lot about these high megawatt, what we consider commercial, sort of energy center type wind farms. But there's a lot of technology out there that's more distributed generation type, smaller turbine technology for individual homeowners or for smaller co-ops or for universities or other types of large campuses, whether they're industrial or university education campuses, where they can produce electrons. That turbine technology is changing too. It is smaller than what we consider the large scale turbines. But just because there's large scale turbines on the landscape and they're available doesn't mean that, everybody is using them everywhere. Again, it really drives into what is your wind resource? Where is it most productive? What does your wind regime look like? And do you have existing infrastructure? Right. So there's a question I see in the chat. I don't want to jump ahead, but the question about repowering, can you use existing sites, make them a little bit taller, refit them with longer blades, change the gearing? And the answer to that is yes, right? All of that is yes. It's just a matter of doing the math and making sure your structures are built to accommodate that type of repowering. And it's important too, when we start talking about repowering and the impacts on wildlife. If you take an existing site that has the existing volumes of rotor swept area and you simply increase that, you're adding a very small percentage on top of what was already covered under the rotor swept area. So generally speaking, it's not a huge increase in the risk factor of a site, as compared to going and building that site brand new, right? You've now just created volume of risk where there wasn't before. That was a very long rambling answer, but I'll let Sarah and Eric, I'll take a breath.
I was just going to say, no, it is an interesting question about the minimum. We're talking a lot about what's the maximum height now that we're getting, higher and higher, but while the hub height is increasing, so is the blade length. So there, are cases where you're going to have wind turbines that are going to change their minimum. How low does it go? How low do the blades swing towards the ground? And in some cases, that is going to get lower. I think it depends on the particular model and make of the turbine.
Eric doesn't look like he wants to respond.
I mean, I think they covered it to a large extent. I mean, I think to me, one of the interesting possible trends is to see more varied turbine selection within a given facility, right? So trying to have turbines of different hub heights for specific locations, really trying to get a robust sort of 3D view of what is the wind resource and how do I eke every little extra sort of kilowatt hour or megawatt hour out of that volume of wind that's passing through this facility. And so, yeah, you might want to have different hub heights in different places. And like Sarah said, larger blades, even if you're putting them on taller towers, they might come closer to the ground, but they might not. I think that's both turbine specific, but also site specific. Again, depends on the resource. It's also would be interesting if you're thinking about sort of ground level impacts, like if you have, more dense facilities, do you have the turbines closer together, but then maybe you have fewer facilities. So what does that do to habitat fragmentation and habitat impacts broadly? Again, that sort of fleet perspective versus the plant perspective. all those things are going to be super critical questions to sort through as we go forward.
That's great. Thank you. So we're getting close to the end. So I want to wrap up with a question that's, really easy to answer. No open-endedness at all. It's some pretty heavy sarcasm. What type of process do you each envision to ensure that we can meet our clean carbon future and balance wildlife needs in a timely fashion?
Sure, I yes, very easy to answer. I think that process-wise, and I know this is said a lot, but everybody involved, including the agencies, need to be working on this together. I think, the Wind Wildlife Research meeting came up a lot that, we need U.S. Fish and Wildlife, we need the industry, we need the conservation groups, the researchers, the consultants, everybody at this table. And I perceive I'm a researcher at heart, so you'll always hear me say research, but we also don't want to do research just to do research. That happens a lot too. Wasted money and time on answering a question that maybe doesn't make a difference, I think is also an issue. So I don't have a straight answer that this is the process. If somebody does, I'd love to hear it. But I think things like this webinar, having these conversations, getting people to think about this stuff, people who are much smarter than I am, will hopefully get us to a point where we have solutions.
I definitely don't have the answer really to the question. And I think your last little add-on phrase at the end of "in a timely fashion," like to me, that's the scariest part, because we don't have a lot of time to do this. And I'm a researcher too, and research takes time. And I do think more research is needed, and that's a critical piece. But if we wait 10 years to try and get all the science right, like that's a huge lost opportunity from a carbon mitigation perspective too. And I think from a process perspective, I think one of the things that I am particularly excited about and would like to see more of is, both kind of management at a regional level as opposed to at a project level, because I think that's super important, because we're talking about fundamental sort of nationwide continental scale change. The other piece related to that too is, if you're only analyzing impacts from building this facility on a specific species, you're not really taking into account what happens if we do nothing? What happens if we do nothing as a society? What happens to wildlife and habitat in those cases? And so to me, I think that's part of some conversations, but I think it should be increasingly, grappled with in terms of the trade-off between, okay, well, we can't do this project or we can't do this project, but then that's actually making a decision about what the future is.
I think Sarah and Eric have very, very good points. And I think a wholesale, holistic picture is needed, right? Landscape scale. We need communities to get together, and instead of moratoriums, we need, better understanding of what it is that are driving moratoriums. We get setbacks and distances, and we get concern from different stakeholders, and sometimes some stakeholders have opposing views and perspectives, and reconciling all of that input can be very difficult to do in a timely fashion. And so I think just as a society, we really need to come together and prioritize, right? What is important to us as human beings and human beings in America, right? Is it clean energy? Is it landscape scale resources? Is it clean air, clean water? What is it that we value? Is it warm homes in the winter and cool homes in the summer, right? It's a conversation. It can't be just dictates from one side or another. It has to be a back and forth. And I think the more open dialogues we have, the more forums where we can discuss these questions, as off the wall or as outlandish as some of the ideas may be, but bring them all to the table and really sort them through, the better off we're going to be, right? The more people we can involve and get on board, with this being not a matter of if, but a matter of when, I think is going to be key.
Thank you for those final thoughts. And I want to take a moment to thank you all again. Thank our speakers, Misty, Sarah, and Eric, for joining us today. And thank all of you online for joining us for this important conversation.
Thank you.
Thank you.